Hello everyone and welcome back to Causality with Boris, all broadcasts from SobolevSpaces. In this video you will learn how to find open non-causal paths and how to block them. Then I talk about the 𝗕cie𝗶𝘁𝗵 criterion, a brilliant invention of Judea Pearl. Make sure you watch takeaways at the end. There will be a link to a tutorial on 𝗕cie𝗶𝘶𝗵. As always, I prepared a PDF that goes along with this video. Check out the link in the description and you will see the PDF in your inbox. How to find open and blocked paths? Let's see it on paper. In this diagram, there is only one path between x and y, and it's not causal. The arrows point to opposite directions. Then there is a node Z1 with two incoming arrows. It means Z1 is a common effect of Z3 and Z2. In causality literature, it's called collider. There is a collider, the path is blocked. A path is unconditionally blocked if it contains a collider. This diagram has two paths between x and y. One is from x to Z1 to Z2, then Z3 and y. The other one is x to Z1, u, Z3, and then y. U is a hollow node. It means we don't observe it and can't use it to block the path. But it still could produce covariation between x and y. Here's an important rule. Examine every path separately. Path 1 has a collider, it's blocked. Path 2 has two colliders, Z1 and Z3, so it's blocked too. It can't produce covariation between x and y, even if we can't control u. Here's another diagram. It shows several paths from x to y. One is causal, x to Z1 and y. We don't need to worry about it. There are three non-causal paths. One path is x to u1, z1 and y. Second is x u1, z1, z2, z3 and y. And another x u1, z1, now u2, z3 and then y. Variables u1 and u2 are not observed. And what's the rule? Examine every path separately. Look, path 1 doesn't have a collider. It's an open path. It can produce covariation of x and y. Now, you give it a try. Pause the video and check if other non-causal paths are blocked. That's right. They have colliders. They are blocked. Here's why it is so important to examine each path separately. That one is a collider on one path, but not on the other. That means there is at least one open path in the diagram. Is the association causal? That's the central question of causal inference. Open non-causal paths produce an association between treatment and outcome. If we can find them, we can block them, right? Okay, we've seen an open path. Can we block it? Yes, by conditioning on a variable in a path. In epidemiology, conditioning refers to stratification. Here is the core idea of stratification. We compare outcomes of treated and untreated units within each stratum separately. Within a stratum, stratification variables don't change. Therefore, covariation of treatment allocation and outcomes cannot be due to changes in stratification variables. Let's recap. We see variable z on a non-causal open path between x and y. What conditioning on z means? It's examining the association between x and y for every z value separately. If z is constant for all x, then x doesn't change due to z. If it's the same for all y values, then changes in y aren't due to z. We conclude the covariation of x and y can't be due to changes in z. Let's take a look at this beautiful graph. Here's a non-causal path between treatment and outcome, in red. There's a common cause in it. We don't see any colliders, so it's an open path. To block it, we condition on the variable representing a common cause. Conditioning means stratification by its values. The common cause values will determine individual strata. Within each stratum, we examine association between treatment an outcome. There is no influence of the common cause within each stratum. By stratification, we eliminated the red arrows from the graph. Look here, the non-causal path is gone. In 1976, epidemiologist 𝗕𝗂𝘂𝘂𝘶𝗶𝘂 made it public. The stratum-specific effect isn't due to stratification factors. To get an overall treatment effect, we combine effects over the strata. We talked about blocking paths informally. Judea Pearl developed a graphical criterion for this. Not surprisingly, it involves conditioning. Here is the 𝗕cie𝗶𝘁𝗵 criterion. Conditioning on a set of nodes 𝗕separates two other nodes if it blocks every path between them. In this diagram, conditioning on a set of variables z will block a path if variable m from z is a mediator in a chain A to M to B, if m is a common cause for A and B in a fork M to A and M to B, and if the path contains collider C that is not in Z. 𝗕liche𝗿𝗂𝘂𝘶 put together two rules for blocking paths. First, unconditional separation. Path with a collider is blocked. In other words, arrows that meet head-to-head do not transmit variation. In this diagram, x and y are 𝗕separated because of the collider T. The second rule is blocking by conditioning. Conditioning on a set of nodes blocks a path without collider if these nodes lie on the path. Pearl reasoned x and y are deconnected if a path between them is open. No arrows collide head-to-head. X and y will remain deconnected after conditioning on z if z doesn't lie on a collider-free path between them. Otherwise, we say that x and y are 𝗕separated by conditioning on variable z. Here is the summary of three blocking by conditioning rules. Conditioning on a non-collider blocks a path. That's 1. Colliders block paths. 2. Conditioning on a collider opens path. 3. Let's practice applying them. You see a familiar diagram. It shows a single path between x and y. Let's count sets of nodes that we may consider for conditioning. First, 3 individual nodes, z1, z2, and z3. Then 3 pairs, z1 and z2, z1 and z3, and z2 and z3. And 1 triplet, z1, 2, and 3. And of course an empty set. Mathematical formality, you say? Not really. It's just to indicate we want condition on any node. For each set, let's find if conditioning on it 𝗕separates x and y. Let's start with an empty set, no conditioning. Then x and y are separated by a collider z1. Conditioning on z1 allows the transmission of variation from z2. That's why we don't condition on a collider. Conditioning on z2 separates x and y. The same is true for z3. What about conditioning on the pairs of nodes? For z1 and z2, it's separation, even though z1 is a collider. And actually, it's yes, separated for all remaining sets. Let's practice on another diagram. It shows an unobserved variable u. You know what? You give it a try. Pause the video and find sets conditioning on which would separate x and y. Did you get the same answer as for the first example? Awesome. That's right. We don't observe u. We cannot condition on it. And z3 is not a collider on either path from x to y. What about this diagram? Note that all nodes u are not observable. Then z1 is not a collider for two paths from x to y. So conditioning on the empty set doesn't separate them. Conditioning on z1 or z2 doesn't separate them. Only conditioning on the pair z1, z3, and the triplet blocks all paths. Right, this is it for today's lesson. The main message here: we can block an open path by conditioning on a variable that lies on it. You learned how to identify blocked paths. Our guiding principle is to look for a collider. Look for arrows coming head to head. Colliders block paths unconditionally. Conditioning on a collider opens paths. Then you learned about blocking by conditioning rules. Conditioning on a variable on the open path blocks it. Make sure you watch a tutorial for this video. I'll show you how to explore paths using a fantastic online program, 𝗕cie𝗶𝘁𝗵. Keep on watching.